Section 10.2 Taylor series. What we're going to do today is shorten up the process of constructing a series using the formulas for Taylor series and Maclaurin series. And you will be presented with the 7 Maclaurin series that you need to just know. Whether you memorize them or find a quick way to create them, either way, you need to be able to come up with them rather quickly. So this first slide is what we had the other day when we created our series for sine x, cosine x, and e to the x about x equals 0. We equated derivatives with this polynomial c sub 0 plus c sub 1x and so on. And then we said if we wanted to center this series somewhere else, that we would shift the polynomial by subtracting a from x in each term. Here we just have the definitions of Taylor series versus a Maclaurin series. A Taylor series is the general term, and it's an infinite sum giving the value of the function f of z in the neighborhood of a point A in terms of the derivatives of the function evaluated at A. So this is at any value A. And to be more specific, a Maclaurin series is a Taylor series that is centered at x equals 0. We need to discuss some terminology. Sometimes you'll be asked to find a 7th order or a 6th order or a 5th order polynomial, Taylor polynomial. And what that means is you go out to the term that is created by doing the 7th derivative for a 7th order polynomial. You may also be asked in different problems to come up with a 7th degree or a 5th degree polynomial, Taylor polynomial. In that case, you go out until the power of x, the highest power of x, is the degree that they're looking for. Here we have just a reminder that sine x, cosine x, and e to the x are very special series in that when we create the infinite series for these functions, they overlap the original function for all of the domain. So there is not, it's an infinite interval of convergence, which is not true with most series, but these three are very special in that way. Okay, so now we have our formulas to help us create a Maclaurin series first. And when we created these series on our own, we kept coming up with these factorials that we had to divide by to solve for the constant. So we have this formula that allows us to come up with the series without having to go through the entire process of equating derivatives to find our constants. So you can create a Maclaurin series by using this formula, which is the sum from k equals 0 to infinity. This is the kth derivative at 0 up on top. That is not a power, that's the derivative. So it's the 0th derivative, which is the original function, then the first derivative, second derivative, and so on. And so you can use the sigma notation to help you create your series. If you're asked to find a partial sum, then it's this same formula, but maybe from k equals 0 to something like 5, where you'd have term 0 through term 5. So that's for the Maclaurin series. And then for the Taylor series, which is more general and can be centered anywhere, we have the same formula, but the differences are that each derivative is evaluated at A, not at 0. So that's the difference here. And that our x terms are shifted to be centered at A. So we have the sum from 0 to infinity of the kth derivative, again, evaluated at A, over k factorial times x minus a to the k. So it's just a formula we can use to create the Taylor series. We use this one when we are centered somewhere other than 0. So if we look at our first example, we want to find a Taylor series, find the Taylor series generated by f of x equals e to the x at x equals 2. All right, so using our formula, we're going to need to find f of x, f prime of x, f double prime of x, f triple prime of x, and maybe the 4th derivative. You don't always have to go out to 4. You just want to go out until enough derivatives that you can see a pattern when you're writing your series. So the 4th derivative is a pretty good bet. Then we need to evaluate the original function and all of those derivatives at 2. When we do that, in our formula, that's getting us this part right here. The derivative, the kth derivative, what I'm showing here is that 0. Let's change that to the proper. Okay, so now we have the proper Taylor series here, the one that we use when we are not centered necessarily at 0. So, as I was saying, each of these derivatives evaluated at 2, that gets us this part of the formula. So once you find that derivative evaluated at a, then you put it over k factorial, starting at k equals 0, times x minus a to the k. So our first one would be e squared, that's f of 2, over 0 factorial times x minus 2 to the 0. So that just gives us e squared. Then we let k equal 1, and we get e squared, because that's f prime of 2, over 1 factorial times x minus 2 to the first. And we keep going with k equals 2. E squared is the second derivative here, over 2 factorial times x minus 2 to the second. And then we get e squared, the third derivative, over 3 factorial times x minus 2 to the third. And here is our Taylor series generated by f of x equals e to the x, centered at x equals 2. So that means this series would match the function e to the x as long as we're in the neighborhood of x equals 2. All right, now we have the 7 Maclaurin series that you're going to need to know, and you should write them down. You should find your way to memorize them. I will expect you to know them for any quiz or test or your final or the AP test from here on out. So you'll need to practice those. Part of the homework in 10.2, they have you come up with different functions based on using these as your starting point. So for example, if I asked you to find a series for cosine of 3x using the Maclaurin series as your starting point, then you would go to your cosine x series, which is here, and for every x you would replace it with 3x. So we would have 1 minus 3x squared over 2 factorial plus 3x to the 4th over 4 factorial, and so on. So in the 10.2 homework, you'll be creating series using first the Taylor or the Maclaurin series, creating them like example 4 that we have here. And then the second type of problem, you'll be altering a given Maclaurin series to create your new series. All right, so that should do it. Please make sure you write down all these Maclaurin series that we need to know. Find your way to memorize them.